Okay, so let's continue. So here we'll talk about how to calculate the potential due to a how to calculate the potential due to a continuous charge distribution. Okay, so here we see this charge disk again, but of course in chapter 22, we try to calculate this disk. Okay, so we try to separate into many ring with different radius, and then we integrate from 0 to R, so that if from a disk, and then so we can find the E view. And then if we just let the radius of the disk to be infinite, and then it will be an infinite large plate, and it will generate a constant E view, if you still remember. And then in chapter 23, we also use the Gauss law to verify that if this disk is infinitely large, we can also derive the E to be the same value. Okay, so here, rather than calculate the E, we try to calculate the V generated by this disk. Okay, so we also try to cut it into rings with different radius. Okay, so for this one, with the radius to be R prime, capital R prime, and then R is the full radius of the disk. Okay, so here, let's consider the orange ring. So this is dq. So we will have dq on this ring. And dr is the width of the ring, and then sigma is of course the surface charge density. Okay, so it will be like dq equals sigma times dA. This dA is actually the area of a ring. Okay, so this is a ring, and then we try to cut it out, so it will be like when we try to cut it and then expand it, so it becomes a rectangle. Believe it or not, also, it will become a rectangle. So the height of this rectangle will be dr prime, and the width of this rectangle will be 2 pi r prime. Okay, because it is the perimeter of not the perimeter, the circumference of a circle, so it's 2 pi r, but of course the radius is r prime, so this is 2 pi r prime. Okay, and then the height is dr prime, so the area dA will be 2 pi r prime times dr prime. Okay, which is this one. So this is dA. This is dA. Okay, so this is dq equals this term. Okay, so next. Okay, so we will consider what is dV. Okay, dV will be k times dq over r. K times dq over r, nothing special. So we can plug in dq to here, and then with this variable dr prime. Okay, so we have sigma dr prime sigma 2 pi r prime dr prime, sigma 2 pi r prime dr prime. So this is the dq. And then we have this is k, and then r, small r is actually, let me see, small r. Okay, I think this small r should be r prime instead. This one should be this one should be r. Sorry, this r is not that r. This r is this one. This r is this one. Okay. It means that the distance from the ring to the desired point P. Here we also can only find the V along the z-axis. The z-axis is perpendicular to the disk and go through this center point. So this is really the distance from this ring. Every point on this ring to point P is small r. But we cannot regard it as a known variable because we have dr prime here. So we need to express all variable in terms of r prime rather than small r. Otherwise, we cannot do the integration. It would just like integrating a dr prime with something like r. Then we are not able to do the integration. So we need to have this one to be a function of r prime. This bracket doesn't mean multiplication. This is a function. Like r is a function of r prime, which means that here we should have r to be square root of r prime square plus z square. Okay, according to the Pythagorean theorem. Okay, we have r. So it's like r is actually like r of r prime, which is like r of x or I mean that something is like f of x equals x squared plus r square root. So this is like f is a function of x. So here r should be a function of r prime, and then we plug it there, so that r becomes this square root term. So we should have a prime here. Okay, this one should be r prime square. This one should be r prime square rather than r square. Okay, so in that case, this is a function of r prime. All other variables are constant to r prime, so we can be able to do we can do the integration. Okay, so later on we have v equals integration of dv, and then we plug this one here. Okay, so we can do some cancellation first. So we have a 2 pi and then partly cancel with this one to be a 2. So we have 2 epsilon naught here, 2 epsilon naught. And then we have sigma put in here. So we altogether have a sigma 2 epsilon naught to be here. And then the remaining thing is that r prime dr prime. So we have r prime dr prime. And then we have also this square root term. Okay, also this one should be r prime square rather than r squared. Okay, so in that case, this integration will be easier than the one we handled in the previous lecture. This one is like, we can make this one to be like d r prime square plus z square. Okay, so it is like the reverse direction of the chain rule. Yeah, so if you don't familiar with this one, I can try to rewrite it like d and then r prime square plus z square and then dr prime. Okay, then for this one, this is like a normal derivative. Then this is something square, and then take the derivative will be like 2r prime. Okay, okay. So this one should be like one half of it. Okay, I just forgot the factor of 2. So yeah, so this one should be 2r prime, and then you try to move this one over, then you can see that dr prime square plus c square will be like a 2r prime dr prime, something like this. Okay, z is a constant to the r prime. Okay, so yeah, so we put like that. Okay, so this one becomes one half of this one, and then we can do the integration. If you consider it to be too complicated, you can just do some change of variable, like you can just to make u to be r prime square plus z square. Then this one will look like integration of this one is one half of du and then u to the 1/2 power. So you can just put it to the numerator, becomes 1/2 of u negative 1/2 power and then du. So for integrating this one, you add 1 to the power, so it becomes u to the square root of u, and then divide by 1/2. So the 1/2 and this 1/2 will cancel each other. So this one will become square root of u. So you can see here, we will have square root of u evaluate from r prime equals 0 to r prime equals L. Of course, multiply by by the sigma over 2 epsilon naught, like this. Okay, so here we should have u to be this one. If we put in r prime to be L, r prime, so let me see, r prime to be L, then you will have r prime, oh, not L. Okay, this one is not L, this one should be R instead of L. So it should be R from 0 to capital R. Okay, so here, if you plug in R prime to be R, we have R squared plus Z squared, and then take the square root. So you have this term, Z squared plus R squared square root, and then minus R, this function, the square root of U evaluated at R prime to be 0. R prime to be 0, U equals Z squared, and then take the square root with Z. So you get the second term. So that's why we get this expression. Okay, so we have V to be this expression. And okay, so note that the variable in the second integral is R prime, not Z. Okay, Z is just a constant value. Because throughout this integration, when you change R prime, Z doesn't change at all. But R will change because R prime is changing. Z is keeping constant because this is the point we would like to find for the electric potential. So Z doesn't change at all. The only variable is R prime squared. Okay, so we get this expression. And here we try to come up with this expression. Okay, so it said calculating the field from the potential. So you may wonder why we need to calculate the potential, because the idea is like let me just add a page so we have some place to draw something. Okay, so in chapter 22, what we would like is that given a specific structure, we would like to calculate the E field. In chapter 22, we have the method like we using the integral. We separate integration, integration. Okay, using integration, we try to separate the structure into small element, and then we try to find the dE for each element, and then finally we add them together using the integral. So that's the way we learn in chapter 22. Okay, so this is the first method. And the second method is that we also try to evaluate the E field directly. In chapter 23, we use the Gauss law. So we try to learn something new about the surface integral. So it will be useful for the Gauss law. So to let you understand what Gauss law is. Okay, so using the Gauss law, we are also able to find the E field directly. Okay, but with some symmetrical structure. Here, we have another method. We try to evaluate the V, the electric potential first. Try to evaluate first, this one first. And then after getting the expression of V, we will be able to calculate E from the V with a derivative, like dV, it should be like dV ds. Okay, in one dimension, it will be a simple derivative. In high dimension, it will look like something strange, a upside down triangle of V. Okay, so this one we call it gradient. Gradient. So you will learn this one in multivariable calculus. Okay, so yeah, so this is not that difficult. Although this is upside down triangle. What does it mean? It's just like take the derivative in multi-dimension, like 2 dimension or 3 dimension. And of course, gradient, this term is nowadays very hot because recently we have AI. We have AI. There are neural networks. So to train the neural networks, we usually use a method called the gradient descent. Gradient descent. If you are familiar with, if you are interested in the AI, you may have heard this term called gradient descent. 中文叫做梯度下降。梯度下降。Okay. So yeah, this is an interesting thing. So we will use this method to train the neural network, train the AI. Of course, we will not teach it in the course, but yeah, just let you know. Yeah. So in some of the textbook, they use this kind of a symbol. Yeah. Of course, for other textbook, we're still using this kind of symbol. So the idea is that we try to find another variable first, and then with a simple calculation, then we can come up with the E. So at least when you learn single variable calculus, take the derivative will be easier than to take the integration. And another idea is that to calculate the V will be easier than to calculate the E directly, because E is a vector field. This is a vector field. So you need to consider the direction, so on and so forth. So it makes it more difficult. But for this one, this is a scalar field. So it makes the calculation easier. So that's the point. So we try to calculate the V first, and then we try to take the derivative, and then take the minus sign, and then it becomes the E field in that direction. Okay, so here, the point is like, so here we demonstrate, in this figure we can see there are some dotted yellow line, which means the equal potential surfaces. Okay, so which means that all the E field will be perpendicular to it, just like the E field will be like, this is the E field here, this is the E field there. All the E field line will be perpendicular to the equal potential surface. Okay, so so before we have an expression like V to be negative of integration of E dot ds from I to F. If you still remember, we just learned this one in the previous lecture. So here this integration. So we try to integrate the E field becomes the V. So yeah, so it will just like we take the derivative of V, it will becomes a E, but this is not a normal derivative. So yeah, in single variable, it is like the fundamental theorem of calculus, 微积分的基本定理. Okay, so yeah, so an integration of this one will be this one, and then take the derivative will become this one. Okay, so in multivariable calculus or multi-dimensional integration, and then yeah, this is a line integral, and then this one will become a gradient, okay, which means a high dimensional derivative. Okay, so the idea is like this. So here it says try to come up with this expression. So so at first you try to write, this is the work done. This is the work done if we try to move this charge through this E field. So F dot ds is of course the work done. When you learn mechanics, F dot ds will be the work done. And then this F will be Q0 times E. So Q0 is the test charge amount multiplied by the E field at that point. Okay, so here we also assume that the path might not be a straight line, so we try to cut it into small pieces. So every small pieces we can regard it as a straight line or straight segment. Okay, so F equals Q0 dot E. So we can assume that E is uniform inside or within an element. So we have F equals Q0 dot E, and then dotted with ds. Okay, and then we also have this one. This one is negative du, negative du. At that time, in the last lecture, we write it as delta u equals negative q0 delta v. Okay, so we just replace delta with d. Okay, so we have a negative du equals negative, or we don't have a negative sign here, so it is like delta u equals q0 delta v. So here we have negative du equals negative q0 delta v. Okay, so here we have dv. Okay, so this is work done. This is negative u. So these two should be the same thing. Okay, so yeah. So actually, this one, and then this is a dot product. This is a dot product. So we try to extract it. So E and then ds. So we have E and ds, and then multiply by the cosine of the angle between them. So theta is the angle between the E field at that point and also the ds. ds is the follow the tangent line and then follow the direction of the path. Okay, so here we have q0 E ds and then cosine of theta. Okay, so we come up with this expression, and then we can do the cancellation. q0 and q0 cancel, and then nothing else. So we can just move over this term to the left side. So finally, we get E cosine of theta. E cosine of theta equals negative dv over ds. dv over ds is like take the derivative of v with respect to the s, and then take the minus sign. So we have a minus sign here, similar to this one. So it is like, okay, take the integration of e become v. Here we take the derivative of v, and then it becomes e. Of course, we have a cosine of theta here, but actually this means that this one is the s-axis. This one is the s-axis. Okay, this one. Okay, so e times cosine of theta is like the s-axis component. Es is the s-axis component of e. So yeah, so this is like this. So below we use es to specify e cosine theta, because it means the s-axis component. Sometimes we will use ex to stand for the x-axis component, ey to stand for the y-axis component. So here, generally we call it the s-axis. So we have es equals negative dv ds. Okay, so yeah, so here we try to come up with the reverse version of the previous definition of v. Okay, so generally, if we have x-axis, y-axis, z-axis for the Cartesian coordinate, so I've mentioned this many times, Cartesian coordinate, okay, 直角坐标系或者是笛卡尔坐标系. Okay, so we have a ex to be negative dv dx, or ey to be negative dv dy, or ez to be negative dv dc. Okay, so we can write for 3 dimensions. Okay, and in mathematics we will just write this whole thing with a simple expression. So e is just like e to be ex, and then I hat plus ey, and then j hat, and then plus ez, k hat, something like that. Usually for Cartesian coordinate, we have x-axis component multiplied by the unit axis along the x-axis, so on and so forth. And for this one, what does it mean? So this one, just like I mentioned, this is so-called a gradient operator. Gradient operator 就是梯度的运算符啊，operator. Okay, operator means 运算符. Okay, so maybe in some of the like programming language like C++ or whatever, they will just use the object-oriented programming, then you like some operator. Yeah, or actually, yeah, in the past when I taught ECE for the physics 2, I will teach quantum mechanics, the chapter 38 of the textbook. Then we will have some operator in the quantum mechanics. Yeah, if you have interest, you may try to watch it on my YouTube channel. But of course, in this semester, I won't go to that chapter. Yeah, but if you have interest, you feel free to check it on my YouTube channel. Okay, so this is so-called a gradient operator. So in mathematics, in Cartesian coordinate, this gradient operator will look like I hat and then partial x and then plus j hat partial y and then plus k hat partial z. Okay, so if this gradient operator yeah, usually won't occur independently. Yeah, if it just occur independently, it will just like something not complete. You can see it is like the derivative without this one. It's just like when you are in primary school, when you learn the arithmetic computation, you have plus, minus, multiplication, division. Okay, for this kind of operation, you should have something in the front and at the back, like a plus b. Oh, then you will be able to find, oh, if it is like 1 plus 3, it should be 4, something like this. Yeah, but for this operator, it just follows something behind. Yeah, maybe you can think of some operator only have one variable, like factorial. For example, if you have a 4 factorial, it should be 4 times 3 times 2 times 1. Then factorial can be also regarded as an operator. It is like a 4 times 3 times 2 times 1 to be 24. Yeah, in high school, yeah, probability class, you should have low what is a factorial. Even we can have something like 1/2 of factorial. If you're interested, you can check on the Wikipedia, like, oh, this is so-called gamma function. You can take all the real number, and then you can take the factorial of a real number. So it's so-called a gamma function. Except some maybe like negative one you can have is factorial. Yeah, but yeah, so this is like an operator. But here, this operator, it only followed by the scalar field. So when this operator operate on the for example, this is the potential, is a scalar field, then it becomes a vector field because it is like gradient of v, and then take the negative sign, will be like negative I hat and then partial v partial x and then minus j hat partial v partial y and then minus k hat partial v partial z. Okay, so if you have only learned single variable calculus, you only can find dv dy, and then what is this partial means? So this partial means maybe this v is a function of x, y, and z, but for this one you only consider x is a variable, and then we got other y and z to be constant. So yeah, so when you do the calculation, then it is nothing special. But regardlessly, in mathematics, we should write it as a partial v partial x rather than dv dx, because v may be a function of y and z, or rather a variable. Okay, so yeah, so it turns out that, okay, so this is the vector field, and then we take the derivative in different dimension and then multiply by the unit vector in that direction, and then take the negative sign, and then it becomes the E field. Okay, so if you are interested, you can see the gradient theorem on the Wikipedia, which is actually the fundamental theorem of calculus for line integral. So in calculus class, you should have learned the original fundamental theorem of calculus in one dimension, which is like if you have let me see, if you have an integration of f of x dx from a to b, it should be like f of b minus f of a. Here df dx should be f. Okay, this is so-called the fundamental theorem of calculus. Because when you learn calculus, when you learn the derivative and the integration, the derivative is of course a limit, which is like df dx should be like f of x plus delta x minus f of x over delta x, and then take the limit delta x tends to 0. When you learn derivative, the definition of it should be like this. And then when you learn the definite integral, the definition is should be like a Riemann sum. Should be like a Riemann sum. So the fundamental theorem of calculus tells you that why these two looks like not so related operation should be the reverse operation or the anti operation. So that's why when you do the indefinite integral, then you only need to find the antiderivative of this function. And then that's it, plus a constant, and then that's it. So yeah, so that's why the fundamental theorem is important for calculus class, although you will never use it again. You'll never use it again. So that's only tell you that the derivative and the integration are reverse operation, and this is the the fundamental theorem of calculus for line integral. And later on you will also see the fundamental theorem of calculus for 2D and 3D version, okay, but later. Okay, so so here we have a sample problem. Okay, so just now we just derive the potential for this structure, for the circular disk. Okay, the expression is like this. Okay, so here we try to use this, take the derivative and then take the minus sign, then we can verify that it should be the E field we got in chapter 22. Okay, so here it says the electric potential at any point blah, blah, of a uniform charge disk is given by this one. We just derived it in the previous slide. Okay, so just starting with this expression, derive an expression of the electric field at any point on the axis of a disk. Okay, so this is easy because we try to find easy. As we know, this is symmetric. There should be no x-axis component and y-axis component. So there should only be z-axis component, as we know. So EZ would be, let me change back to blue color. Okay, EZ will be negative partial V partial Z, or you can just write it as a dVdZ because it is only a variable of Z. So yeah, so this is, so we just try to plug in this expression. And then this one is a constant to Z, so we can just put it outside. And then we can take dz for square root of z squared plus r squared minus z. Okay, so we have negative sigma over 2 epsilon naught. And then take the derivative of this one. This is like a z squared plus r squared and then to the 1/2 power. So taking the derivative will be like 1/2, and then this one, the power minus 1 will be like a 1 over square root of z squared plus r squared. Okay, and then don't forget the chain rule, which means that we also need to take the derivative of this inside function. Okay, So we need to take derivative with respect to this one. So c squared, take the derivative, will be 2z, so we have 2z here. And then r is a constant to z, so taking the derivative will become 0, okay? So, and then minus dz will be 1, okay? And then finally, we can do some cancellation. These two and these two cancel. And then finally, we will get, so we try to distribute this negative sign inside. So we have sigma over 2 epsilon naught. And then this is positive, so we put it first. So 1 minus z over square root of z squared plus capital R squared. Okay, like this. And then in chapter 22, we already derived it, actually the same expression. So if you still remember, when we try to do this one, okay, the integration might look more difficult, So the idea here is that we try to come up with this expression of v with an easier step, and then we try to take the derivative. Then we can get the E field. So that's what I explained on this page. So we can directly calculate it if it is easy enough. Otherwise, we may be able to find the V, the electric potential, in an easier way, and then take the derivative in different direction, and then we can get the E. Taking derivative will be easy. Okay, calculating this one is also easier. Okay, so it may be easier for us to do it like this, although this path may look longer, but yeah, maybe this one is a possible way to do that. Okay. Okay, so so let me still continue. So here we talk about the electric potential energy due to a charged particle. So here we try to evaluate the electric potential energy for some structure with some charges. So it says the electric potential of a system of charged particle is equal to the work need to assemble the system with the particle initially at rest and infinitely distance from each other. Okay, which means that originally in the system there is nothing, there is no charge at all, and then we try to put, for example, if we have n charges, we try to put one there. So when you put the first one, you don't need to do any work because there is no E field at the very beginning. So when you try to put it, you don't need to do any work. And then when you try to do the second one, then you need to do work because for the first one is there and then it already generates some E field. So if you try to move a charge near it, then you need to do some work, and then so on and so forth. If you put the third charge there, then according to the first and second charge, it generates some E fields, and then when they add together, and then so you need to do more work. So in that case, between every two charges, there will be some energy stored. So when we try to calculate the energy, also before going to n charge, for the two particle case, at separation R, the energy will be U equals 1 over 4 pi epsilon. This is K times Q1, Q2 over R. Okay, so far we have 4 variables with a similar structure. Sometimes it's Q1 times Q2, sometimes it is only Q. Sometimes it is R, sometimes it is R squared. At least so far we have 4 variables. One is F, one is E, one is V, one is U. Okay, so there are 4 combinations. Two of them have Q1, Q2 in the numerator. 2 of them have Q in the numerator. 2 of them with R squared in the numerator, denominator, and then 2 of them have R at the denominator. Okay, later on I have a page summarize them. Okay, so this is the case for two particles system, and then if we have multiple particles, then we need to consider the total potential energy of a system of particles is the sum of a potential energy for every pair. Okay, every pair of particles in the system. So if we have n particles in the system, we should have totally n choose 2. This is one of the notation. Some of the textbook might use NC2 or NC2. I don't really know which one you have learned, but it means that it should be like n times n minus 1 over 2, or n factorial over 2 factorial minus n minus 2 factorial, something like that. Okay, so but at least it should be n times n minus 1 over 2. It would be like, for example, if it is like there are four, let me three. Okay, so this is I, this is J. So 1, 2, 3, 1, 2, 3. Okay, so in that case, 1 and 1 shouldn't have any potential. 2 and 2, 3 and 3 shouldn't have any one. So maybe you can either choose this triangle or that triangle. So if we choose the upper triangle, then we also don't consider that one. So we have 1, 2, and 3. So for 3 choose 2. 3 choose 2 is 3 times 2 over 2, which is 3 terms. If we have a 4 charged particle, it should be 4 choose 2 will be 4 times 3 over 2, which has 6 terms. Okay, so yeah, if the number of charge increase, then yeah, it will start to increase. Okay, so this one look like horrible, but actually you can just try to count it like this. Usually in the exam, it won't be too large number. Maybe 3 or 4 is the maximum. So even for 4, there are at most 6 term only. So this sigma means I is not equal to j. You try to go through I from 1 to n, j from 1 to n, but I cannot be j. And if I and j exchange, then you don't count twice, which means that you don't count I to be 2, j to be 1, and then count I to be 1, j to be 2 again. So you only count the upper triangle. So here, let's see a sample problem before we have a 0-minute break. Okay, so here, let's see. So it says 3-point charges held in a fixed position by forces that are not shown. Okay, of course, if we try to fix it there, then of course there will be some forces either attracting or repelling them. So if you need to fix them, then there must be some external force to fix them. Okay, so yeah, so that are not shown. So what is the electric potential energy U of this system of charge, assuming that D equals 12 centimeter, and that Q1, Q2, Q3, in which Q is 150 nanocoulomb. Okay, so here there is only 3 charges. So U equals U12 plus U13 plus U23. They are totally three terms. So in that case, we have a K times Q1 times Q2 over the distance between them. Okay, so this is a equilateral triangle. So all the distance between every 2 charges are also D. So this is D, and then plus U13 is Q1 times Q3 over D, and then plus U23 is a Q2 times Q3 over D. Okay, so that's easy. Okay, so so all the D are common factors, so we can have a K over D, and then we have Q1 Q2 plus Q2 Q3 plus Q3 Q. Okay, let's try to write it as a Q1 Q3 Q2 Q3. Okay, like this. So we can plug in the number. K is 8.99 times 10 to the 9th power. And then D is 12 centimeter, 0.12. And then Q1, Q2. Q1, Q2 is 1 times, okay, we just put this Q outside. We have Q square outside. So we just need to consider how much Q we have. So Q1, Q2 is 1 times -4, and then plus Q2, Q3, -4 times 2, and then plus Q3, Q1 is 2 times 1, 2 times 1. Okay, maybe you just reorder it. So this is Q2, Q3 plus Q3, Q1. Yeah. Okay, so and then multiply by 150 times 10 to -9. Nano is -9, 10 to -9, and then quantity square. Okay, like this. Okay, so this should be a negative number because this is -8, -4. So -12 plus 2, so it should be -10. So it should be a negative number, equals -1.7 times 10 to -2 joule. Okay. So this will be easy because this is just a scalar addition. Okay.